do the verification of the data which we have collected, and the end goal is to identify the root cause contributing to the failure. This is a typical fishbone diagram which we just discussed about. This is the weld failure. So weld failure can be because of environment, methods, machines. So further sub causes which I was talking about, for example, for material, the sub causes can be welding electrodes or filler wires or welding gases. You can identify few others and you can add on to this and then study each of them and try to find out whether they had contributed to the failure or not. So this is a typical fishbone diagram, but this can be modified based on case to case. Failure mode, effective effects analysis. It helps us to understand and reduce risk by examining possible modes and their potential sequences. I'll just suggest you to go through this slide quickly because we need to finish this different techniques of RCA, and then we'll go to the main subject of failure analysis itself. At the end of the presentation, what I'll do is I'll also share the notes for the webinar so that you can keep them handy to refer for the failure analysis, how you have to conduct a failure analysis, and it all will cover these slides. The next one is fault tree analysis. Again, rushing through this. Just bear with me. The last one is the 5 why analysis, in which we ask 5 questions related to the failure. Ask 5 times why, and we arrive at the cause of failure. This is an example. Why did the machine break down? Because the motor was overheated. Why was the motor overheated? Because the cooling system failed, and so on. And finally, we arrive at why the bearing seized, because it was not lubricated.
Why did water overheat?
Coming to the factors which contribute to the failure. There are different factors which can cause the failure. There may be some other causes also which you think are the causes, but they are subcategories. You can consider them to be the subcategories to these failures. For example, the failure can be mechanical or chemical or corrosive, thermal, radiation, or electrical. Root cause analysis has different levels. So what we see is on the right hand side is a tree. What you see is the systems and indicators or the equipment you see here. And there are some evident causes of the failure, which you can see very easily. But there are several causes which have caused the failure, which are the root causes, which are below the ground. You can't see them. So RCA is to identify those root causes. So there are three levels of root cause analysis. One is the physical root, which is pertaining to the equipment. And many failure analysis stop at this level. Uh, and the results are from lab
Wala deh.
investigations, engineering analysis, and it often involves
Kenapa belum?
component level findings and the material level findings.
Oh, nanya apa?
Then the
Apa?
second level of root cause analysis is the human root,
Apa yang ada?
which focuses on the people and the factors, uh, causes of failures linked to the human
Kenapa
elements.
kan?
Examples, wrong judgment made by a
Kayak nama hijau
operator.
pun udah. Bonnya pasti
And
banyak.
the final level of the RCA is
Pas orang tapi kan pas
cause of
lagi milih
human
mata
error.
kuliah kan.
Why human error happened?
Kan biru
So it
harga-harga
can be
biru.
because of the
Jadi perkiraan
organizational or
baik kita nih.
procedural
Begitu
roots,
pas kemet
something
tak
related
sampai
to the
betul.
procedures not
Kalian
followed
jebret
properly,
maling, waduh.
or it can be because of the
Berapa lah?
factors outside
Sama
the
belum
control.
putih yang pertama kali.
For example,
Dua kali
stresses a
masih ya.
an operator is having at personal level, which is affecting his operations.
Tapi ya masih mending meter
So this
33
is an example.
barengan.
For example, physical
Mantap.
root cause is corroded pipe leading to leakage. So this is done pertaining to the equipment.
Ternyata saya tak
And
kometnya
then the human
meter 7
root
ya.
cause is technician not wearing proper,
Dua kan
not
begitu.
following the proper procedures. So it's a
Orang cuma
procedure issue. And the final is the latent
tapi
root
bakalan
cause, which is
grup corrosion engineer mana?
inadequate training. The
Pada
operator
rajin
was
belajar
not
kafe.
trained properly to perform that
Tapi masih pada
operations.
komet kali ya. Kan
We
masih
will
masih
go in details
bener kuliah mah
related to the
mata-mata kok.
first part of the
Iya.
root,
Nah,
the first level of
orang yang
root, which
ngomong
is the
gitu.
physical root,
Tapi makasih orang
because that's the one
lebih
which we
baik
will
ya.
be
Pada
covering
ngomong gue kenapa
in
ya?
the failure
Pada
analysis.
rame.
So physical root causes can
Waktu
be
gara-gara
design
daftar baru mau ngomong
deficiencies,
baik.
material defects, manufacturing or installation defects, service life anomalies. So design deficiencies, to start with the first part, some
Untuk
typical
ngomong ingat ini. Di
examples are
anu
sharp notches
tinggal
causing
ngomong
stress
ini nih.
in a keyway,
Kumpulnya terserah
or
misalnya
small
KTM
radii
engineer
on
gitu.
bearing journal shafts,
Males
all,
ketemu kalau
or
gitu.
residual stresses from complex heat treating designs. Or another example can
Sumpah,
be assembly stress from unwanted interference.
bayar lah.
The second
Cuman
one,
gue bang Epir
the
ngomong.
second one, we'll cover all these four one by one and cover few examples of these. The second one is the material defect. So in forging, there can be different defects like lapse, segregation, cavity, shrinkage, inclusions, etc. For the castings, can be cavity, shrinkage, segregation, etc. Plate can have laminations or cracking or extrusion defects like steps, seams. So this photograph is typical of a lamination you can see in a plate. And this is a forging bus. The manufacturing or installation defects we will cover in different levels. First is the during metal removal process. The typical examples are damage from rough machining or issues from wrong speeds, cracks from electrical machining, grinding damage, and cracks from overheating.
Terus apa?
During the metal working process, the different examples
Benar.
are
Oh kayak mau
deep
ortodoks.
drawing
Itu karena
damages,
sup anu
laps from thread rolling,
ayam
marks from tool use,
benar.
or cracks from flow forming, damage from shearing actions. or overheating in spring
Baka
making.
melu webinar kayak kenen, kok bakal di postingan or apa? Di YouTube.
During the heat treatment, the typical examples of defects are grain growth, quench cracks, decarburization, untempered martensite, inadequate precipitation, sensitized microstructure, inhomogeneities in the microstructure. During welding, the different defects are lack of fusion, cracks, brittle cracks in HAZ, residual stress cracking, slag inclusion, crater of fusion zone at endpoint, filler metal contour out of specification, hot cracking, cracking at low exposure temperatures, hydrogen embrittlement, liquid metal embrittlement. Manufacturing defects during the cleaning or finishing, the examples are hydrogen embrittlement due to plating or corrosion due to inadequate cleaning, intergranular attack or hydrogen embrittlement due to acid cleaning, stress cracking
Inadequate.
from caustic autoclave. And during inspection, typical examples are arc burns due to the magnetic particle inspection, or fatigue or quench cracks, or intergranular attack or embrittlement due to macro etch. And during the final assembly at factory installation site, the different defects can be because of misalignment, missing wrong parts, improper fit ups, improper fastening,
Percaya kok.
inappropriate fastening
Dah, dah,
systems,
dah, dah, dah. Dah,
improper
dah, 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 dah.
tools,
Dah, 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 dah.
inappropriate
Kamu semuanya ke sini.
modifications,
Nangkap ya, besok ya.
inadequate surface preparations.
Mana?
The service life anomalies,
Udah lama ya?
the examples
Hmm?
are listed here.
Udah lama kayak lama ya? Sini.
One is the
Iya.
exposure of the product to aggressive
Ada.
environments.
Emang masih Padang kan ada?
Then the
Terus mana?
improper maintenance example is the welding repair
Hmm.
causing
Oh, iya sekarang.
microstructures which are
Oh,
detrimental
kok di kamar nih emang?
or inappropriate
Wajib-wajib di kamar
modifications.
kabeh.
There are different type of failures. The failures are
Hey,
categorized into the following:
enak.
ductile and brittle failures,
Hmm. Mana SB ya? Iya.
then the
Makan yang
corrosion
banyak.
failure or the
Makan yang
fatigue
banyak kali.
failure or the
Makan yang banyak.
elevated temperature
Sehat.
failures or the wear failures. We'll go through these one by one very quickly. The ductile and brittle failures, the brittle fracture characteristics are they will have minimum plastic deformation or no permanent deformation before breaking. And they generally are associated with high hardness and strength and low tolerance for discontinuities. And fracture happens below the material's yield strength. The characteristics for ductile are significant permanent deformation before breaking, and failures are sudden and Sometimes they are catastrophic and are more common examples of ductile and brittle failure on the top right. Corrosion failures, there are 9 commonly referred failures. One is the aqueous uniform corrosion, then the galvanic corrosion, pitting corrosion,
Apa itu ada?
crevice corrosion,
Hmm.
environmental induced cracking,
Sudah, ano wajib lagi?
hydrogen damage,
Ya, cuma itu aja.
de-alloying or
Lagi siap, siap, siap.
dezincification,
Udah makan yang banyak ya.
and erosion corrosion.
Makan yang banyak.
Other corrosion categories which you would have heard of
Bye bye.
are
Assalamualaikum.
subsets of these corrosion phenomena. In addition, there are corrosion mechanisms, which I just mentioned. MIC is the pitting corrosion happens. We have pitting corrosion, and stress corrosion cracking is a subset of environmental induced cracking. Fatigue failure results in fracture from repetitive or fluctuating stresses below the material's tensile strength, and fracture progress from tiny cracks due to fluctuating stresses. So there are 4 steps of progression. Step 1 is the repetitive load level loads induce submicroscopic changes in the metal structure. Then over a period of time, these changes lead to the formation of small cracks which grow with a continued cycle. The third step is the fatigue fracture propagates from high stresses with fewer cycles or low stresses with many cycles. And finally, it results in the fracture of the component. The fracture component can exhibit both brittle and ductile nature. And the stages of fatigue failure are crack initiation, and then the crack propagation, and finally overload failure. So this is a typical representation of a fatigue failure in which you have initiation point, fatigue crack propagation, and finally the failure. Elevated temperature failures, the effects are because of the increased temperature, initial decrease in mechanical strength, increase in ductility, and we do the heat treatment to achieve recovery or precipitation or grain refinement or homogenization, so that we don't have detrimental mechanical properties which result in the failure of the component. This is a typical exhibit of elevated temperature failure. The drawbacks of excessive time at elevated temperatures, they cause harmful phases. They cause the grain boundary precipitation, grain growth, overload failure, and mechanical properties are weakened as melting point approaches. The wear failures finally uh, are caused by the removal or displacement of surface material and occurs through contact and motion with solids, liquids, or gases, are significantly influenced by fabric friction and lubrication. The consequences of wear failure are loss of material and load bearing capability, increased adhesion and friction, and generation of debris. And the controlled wear, which is an example is automotive brake pad, is intentionally wearing to have controlled wearing. So wear as a failure criteria depends on the component's performance criteria. Failed diesel engine, for example, bearing diesel engine bearing uh, can be due to excessive wear affecting crankshaft movement. Example, this is exhibit of a wear failure. Now we come to the analysis part of the failure analysis. Before we start the failure analysis, few preconditions or pre-analysis considerations have to be taken into account. We need to understand that nobody is an expert in all the areas. It's very normal that a person uh, knows one part of the subject, but he does not know the other process operations. He cannot be an expert of the process. So it's not that uh, the person doesn't know anything about the failure analysis. So if somebody says that I'll have to refer to somebody because this is a process related failure, you have to give credit to him. If somebody is trying to say that he knows everything, yeah, this is nothing, this is very straightforward and all, then he's either misguided or he's misleading. So gathering information is very important, and you have to do the gathering of the information with an open mind. You shouldn't have any biases when you're doing the gathering of information. And during the information which you gather at site, you have to do the background checks, because these background checks often lead to the cause of failure. You can get a hint from there. And avoid biases and premature conclusions. Complete the investigation thoroughly and then make a conclusion what is the cause of failure. Understanding the failure mechanisms. This point, the first point, is very important, because as a failure analyst, you should be having a deep grasp of the different failure mechanisms, because unless you know what are the failure mechanisms which can be uh, prevalent, you can't judge what's the cause of the failure. There has to be correlation between specific features and potentials, causes become clearer with knowledge and experience. So there is no shortcut to experience. And it's acceptable to refer handbooks, standards, and other resources, which all these standards are available at hand. So there is the failure analysis is not a closed book examination. You can refer n number of standards or specifications, and if you want to give a reference to those standards in your report, it will be in fact very much appreciated by the client. We will go through the process of failure analysis. First step is to receive the RFQ or request for for quotation. We have a discussion with the client or site. We make a site visit or discuss over the phone. Then a project is set up. Project is assigned to the right failure analyst. And the fifth step is a review of the failure problem, and we develop the scope of work. So at that time, the quotation is prepared and sent to the client for review, approval, and then once the approval is given, we proceed further. So the first 5 steps, 1, 2, 3, 4, 5, are what we call gathering of information. So this is the first step of failure analysis. There are 3 steps of failure. In the second stage, we initially do the visual examination and microscopic examination, and then perform chemical analysis of the deposits. If there are deposits, we do the XRD or XRF as as in as required. Then we perform the non-destructive testing, ultra UT, MTP, TRT. And if non-destructive testing is not required or is required, after that step, we go to the fractography by SEM. Then we perform the metallurgy, optical using an optical microscope, then material composition of the failed component by OES or FTIR if it is a coating, etc. Mechanical testing, tensile, charpy, hardness, the Rockwell, Brinell, Vickers. So all these steps. One important point to be noted is these steps, although I mentioned in this sequence, the sequence may not be exactly in this same way. It depends from failure to failure. In this particular case, I've just mentioned about these particular tests, but there may be some other tests which are required as per the failure analysis requirements. So they fit in into this flow chart, and the sequence can be altered. But obviously, for example, mechanical testing cannot happen in the beginning, because once the mechanical testing happens, you have already cut and destroyed the sample. So that has to happen only after these steps have occurred. So you have to be careful. You have to analyze which step has to be performed in which sequence. As a failure analyst, it is your responsibility to perform these in the right sequence. So the second step is what we call the laboratory testing part. And then the third, we go to the additional testing as required. Um, we do the conclusions and interpretations after compiling all the results here, what we have gathered from here, as well as what we have gathered from the background information. We compile these, do analysis, and do conclusions and interpretation. We make a draft report, submit it to the lab manager or quality review for quality review, and through the report and retain the samples. The samples are stored for a period of 1 month to 3 months as required by the client or requested by the client. And also it depends on the company's retention policy. So this is basically the complete cycle of failure analysis. And the third step is compilation of test results and interpretation. And interpretation. We come to the first stage of failure analysis, which was gathering information. So information about the failed component, all these have to be taken note of, like location, date and time of failure, function of the item, service life at the time of failure, any deviations, rating like frequency of loading, and any abnormal or normal loading cycles, what material was used, what was the standards, what was the manufacturing standard or specification to which the component was made or fabricated, whether it was operating at normal stresses, temperature, pressure, speeds. So we have to make a note of the operating temperature, range, pressure, and compare what was the design requirements and what was the maximum at which it was operating, strength and toughness, heat treatment, fabrication procedures like welding, adhesive joining, coatings, boltings, inspection techniques. What were the inspection techniques which were adapted in the past during the commissioning or during the stage-wise inspection, during the service and the maintenance, and you have to check the service and maintenance records. Temperature, pressure, position, external influences like air, water, and environmental conditions. So you need to review if the failure is associated because of these. You have to consider these also as part of the analysis, like what was the water quality, etc. As built drawings and photographic evidence. So photographic evidence, if available from the site, uh, and it is you can go to the site and get first-hand information. See the point photography. Most some important points to be considered when obtaining information from this customer. You have to tell the customer why you are doing the interviews and maintain confidentiality wherever possible. Interview individuals or small groups, but don't interview a supervisor in front of the manager. Make the interview comfortable and ask open-ended questions, and do not guide for the responses. As I mentioned earlier, we are supposed to do the investigation unbiased. So we shouldn't be having biases in mind that this was the cause of failure, and we try to influence the operator that was it not because of this. Like these are the very closed end questions. So you're not supposed to ask closed end questions. And difference distinguish between the first hand and the second hand knowledge. Gather specific quantitative data, qualitative data, and opinions. Get referrals and recognize biases when interpreting answers. So, if an operator or a manager is trying to give his biased opinion, that, for example, a manager says, no, in my view, the failure is because of overload, because the material was not meet material was not okay, it was not meeting the specification requirements, and that's why it did not take the load and it failed because of overload. So this is a bias from the manager. Fact might be something different. Do's and don'ts. You have to locate the origin of the fracture, have both the fracture surfaces in undamaged condition. This is a case when there is a fracture failure. If it is undamaged condition, it means that it does not have fracture faces. Fracture surfaces must be protected by tape around the fracture surface, and don't the fracture surfaces should not be tried to be touched to each other. You are trying to abrade the surface and remove certain fluids that are important in SEM analysis. And don't do careless and make sure the destructive testing is planned in advance, because this is self-explanatory. It's a destructive testing. So you can't join back the material once it is cut. So alterations like cutting, drilling should not be rushed into. Prioritize actions that can be undone or reversed. So destructive testing should be in the end. So preliminary examination of failed part. First, do the visual examination to determine the to identify and capture the features of the failed surface. You get to know the origin of the failure when you see the fracture surface, or you can see the stress concentrators. You can see any temper, color, or scale on the fracture faces, orientation and magnitude of stresses, failure mode and mechanisms. By visual examination, you can make a guess of. I would say that this guess word is just for initial examination. You are not supposed to use that guess as the cause of failure. It gives an indication or a hint regarding what could have gone wrong, or direction of crack propagation and sequence of failures, presence of contributing imperfections. So this during this step, high resolution photographs are taken of the failed component, and every observed features are noted down as mentioned above. Taking photographs in as received condition. You can see these three photographs. So it is important that variation in the direction of light source is captured. So these are the three photographs of the same fracture surface at different angles of illumination. So you can see different features at different angles. So when you do the initial visual examination, you have to capture these so that whenever you are doing the further investigation, you go through these features, because one photograph might show a certain feature which is not evident in the on the other photograph. In visual examination, the typical examination features examined up to 50x magnification are, there are two types of failure: instantaneous or progressive. Progressive happens over a period of time, and instantaneous is immediate because of ductile overload or brittle overload. And the typical features which you see uh, in them are mentioned here. Like for ductile overload, you see necking, you see dull fibrous fracture or shear lips. For corrosion, you see general wastage, roughening, pitting, or trenching. Stress corrosion and hydrogen damage may create multiple cracks that appear brittle. For fatigue, you can see beach marks on the surface, progressive beach marks. I won't be able to touch on different aspects in detail because a failure analysis uh, full-fledged course itself is 3 to 4 days. So in that we talk about details of what is fatigue and what are the beach marks, what are striations, etc. So you see ratchet marks, and overload zone is also seen in fatigue failure. So these are the typical features you see in different modes of failure. We do different type of NDT. The NDT specialist in this group would easily identify what are these. Mechanical testing. So this is a typical tensile test. For those who have heard of the tensile test, I'll just have a very quick video on it so that you understand what is done during a tensile test. We should be very careful while interpreting the mechanical test results, because sometimes, for example, the value of a tensile, the material specification says that the tensile strength should be 500 megapascal, just an example. So if the material has 5 to 10% below the minimum specified, if it is say 475, mean that the material is defective or material is wrong, because cold working of that material could have uh, compromised the mechanical strength of the material. Ideally, you should be testing the material which has been unexposed to the environment. We'll go through a quick video of mechanical testing. Impact testing is another one in which we have a pendulum or a hammer which strikes a specimen of 10 by 10 by 55 dimension. Subsizes are lower based on the actual thickness of the material, and samples are prepared or specimens are prepared as per ASTM E23. There are different standards to which specimens can be prepared. There are ISO also. So ISO also has the same size, in fact 10 by 10 by 55 full size specimen, where the sample is broken with this hammer, and we note the energy which is required to break the sample. Another video of Charpy, a quick one. This is the last video we have. My apologies. I was told that the audio wasn't working. So we apologize for the inconvenience. Hardness testing, we have different testing methods. Brinell hardness, mm, Rockwell hardness. The hardness is done to see the resistance of a material when it is penetrated by hard and sharp element called indenter. So we have Brinell, Rockwell, and then we have a Vickers hardness. In most failure analysis, the interest of determining the hardness in carbon steel lies in correlation between the hardness and mechanical strength. There is a correlation between the two, and the usual formula which is used to correlate between the ultimate tensile strength and Brinell hardness of the material is UTS is given by 0.45 HB in kPa or 3.1 HB in megapascals. Scanning electron microscope is used where we do the scans by fine electron beams on the surface. The brightness in the image correlates to the intensity of the signal at a specified sample point illuminated by the beam. And SEM is valued for its speed, flexibility, simplicity, minimal sample preparation requirements. EDS most of the time associated with SEM is when we have deposits on the surface. Clients want to know what are the deposits, or as a part of the investigation, it will be required for you to understand what are the deposits on the surface which could have contributed to the failure. And results are semi-quantitative, and we identify the microstructural phases also as a part of the EDS. We detect the contamination, we identify the corrosive deposits. XRD is another method, X-ray diffraction method is non-destructive to analyze the structure of crystalline materials. And it is used to identify the crystalline phases present in material and therefore thereby reveal chemical composition. OES is used for chemical analysis of the metal of metallic samples. A small portion of the sample is taken and analyzed using OES, optical emission spectroscopy. Microscopic examination involves
Excuse
removal
me.
of a hello.
Excuse me. I think you are still in. Ah, that's good. Now is the slide. Thank you.
Yeah, is it okay?
Now is okay. Yeah.
All right.
Some slide I think is
All right. Thank you. We have small sample of 5 to 15 millimeters, and it is polished, and then it is etched with the different etchants. For example, for carbon steel, or for we have a typical etchant called nitrile, which is 2 to 10% nitric acid in ethyl alcohol. And there are different procedures, different unique etchants for different material. And ASTMs give a typical etchant for different material. This is the microscope is the most important equipment for metallurgists because it helps us to analyze the microstructure of a component. Different phases and inclusions are identified, and heat treatment conditions can be established seeing the microstructure, and we can predict the material behavior under specific conditions. Final determination of failure. This is the most important stage of failure analysis, where we collect all the background information, visual examination, mechanical testing, SEM, chemical analysis, and hardness service, and then we correlate the different aspects, and we try to establish the cause of failure. So interpretation becomes the most important part of this. Mind you, as I told earlier, this is just the lab testing aspects of the failure analysis. So when we do the process analysis, also inclusive, when we analyze the process, we analyze the human factors, other factors, and go to the root, then we talk about the root cause analysis. So joining the dots and interpretation becomes the most important or important factor or aspect of failure analysis. The last but not the least is doing the interpretation. So I'll just discuss two examples for the interpretation. First example, for example, a component which has failed is stainless steel, and you come to know that the exposure and the operating temperatures were between 315 to 540 degrees centigrade. This information you get from background. Then the material is 400 series SS, or it's a duplex stainless steel or austenitic stainless steel. And when do you do the lab analysis, you see the features that the impact specimens have failed or bent specimens have failed. And the material is having high hardness. And normally in metallography, you don't see any abnormalities. You get do the interpretation that the cause of the failure could be because of 475-degree embrittlement. Second example, you see localized pitting or localized corrosion, and you see you observe that the component is subject to cyclic stresses, and cyclic stress concentrations are there, or there are different frequencies of cycles, and failure has occurred at a lower stress, at fewer cycles. The crack initiation has started. When you do the visual examination and the macro or micro examination, you see that the crack initiation has occurred at a stress concentration like a pit, for example, a pit. And the units, the typical units from where you have got seen these failures are rotating equipment or deaerator or cyclic boilers. And the features when you are seeing like its fracture is brittle and the cracks are straight, transgranular and unbranched, and you can see multiple parallel cracks. Cracks may be tight in appearance and may be filled with corrosion byproducts. And the initiation of the crack has been noted from the one typical pitting, and the inspection has been noted by the cracks have been noted by MTPT or UT. You can conclude that the failure of the component was probably as a result of fatigue initiating because of corrosion. So you can say corrosion fatigue. We'll come to a case study. This is a failure which was failure analysis which was conducted on cracked female rotor blades. After 3 to 4 days of commissioning, the high shaft vibration of the female shaft was noted, or rotor was noted, and the air compressor was stopped to examine visually, and cracks were noted on the rotor blade. At the time of commissioning, the vibration analysis was conducted, and trip setting parameters and other operational parameters are mentioned here. The material was 13 chrome, 3.8 nickel, and discharge air compressor temperature was 212 degrees. Discharge pressure was 10.5 bar atmospheric. The rotating speed was 2383 RPM, and it was noted that it was rotating at much lower than the first critical speed of 6498 RPM. So as part of the investigation, background information already gathered, visual examination was carried out, dye penetration, sectioning, and further visual examination. So initially, visual examination is carried out of the sample which was failed. In general view and photographs of the as received condition. Then dye penetration to see if there were any cracks. So cracks were noted. The location in the vicinity of the crack and the locations which were suspected to be the crack initiation points. A sample was taken from that particular location, sectioned and further examined. Tensile and of the parent material of the blade was done, and the splitting of one typical crack was done to evaluate the fracture morphology. Microscopic the vicinity of the cracking was carried out. Chemical analysis of the parent and the welded sections of the rotor were analyzed. And Sharpie impact was carried out, hardness, scanning electron microscopy, and oil analysis, which was used in the compressor. So finally, after getting all these results, the results were compiled and test results interpretation was carried out and conclusion was made. During the visual examination, the welds were welded to the blades were noted to be welded, and sharp notches were noted on the weld groove. So on this right hand side photograph, you can see the sharp notch which was associated with the weld. So very fine linear crack was noted, each of the blade that extended across the full length of the blade and was originating from the sharp notches. So, and during the examination of the fracture surface, beach marks and ratchet marks were noted on the fracture surface. Dye penetration revealed presence of several cracks on the surface. Tensile test did not identify any abnormality. The material was noted to be compliant to the specifications. The microstructure was comprised of martensite. Grains were noted to be much coarser in the parent material when compared to the weld and heat affected zone. And chemical analysis was compliant to the specifications. Sharpie impact values were noted to be compliant to the specifications. Hardness was noted to be significantly higher on the weld in comparison to the parent material. Scanning electron microscopy was carried out of the fracture surface in the location of the fracture very near the notch. And it was noted that since there was no deposit, EDS was not considered necessary for the investigation. As a part of the SEM, it was noted that we had very distinct striations on the fracture surface. So interpretation of the results, compiling all the results, the evidence of high hardness, notch as a stress razor, and striations in the SEM analysis, oil, all pointed towards the cause of the failure as a result of fatigue. Last couple of slides coming to the skills needed for effective material failure analysis. You should have thorough knowledge of material science, of metallurgy, phase diagrams, and behavior under stresses. A failure analyst should be proficient in electron microscopy and optical microscopy, grain boundaries. He should be aware of the different phases expected. And he should have in-depth knowledge of various damage mechanisms like corrosion, fatigue, wear, and creep. The analyst should have fractography skills to be able to analyze the surfaces to determine the fracture modes and the initiation point. Should be familiar with the chemical analysis techniques like elemental analysis or spectroscopy, mechanical testing, knowledge, proficiency in conducting the test or analyzing the results of tensile, impact, hardness, and other mechanical testing techniques. Should have knowledge of NDT, and for the root cause analysis, uh, should be able to analyze the process to identify what's the primary cause of failure. Should be able to do the corrosion analysis, like corrosion mechanic to understand the corrosion mechanisms, included galvanic and crevice corrosion. Fatigue analysis should be something he should be familiar with. Wear mechanisms as well, and thermal analysis. Should be having proficiency in statistical methods, and should have skills in documenting findings, creating a detailed report and recommendations. Should be having good communication skills, and should have industry standards awareness, familiarity with the relevant industry standards and regulations related to metallurgical analysis, and should be able to do the problem solving. And continuous learning is something which is required by a failure analyst. He should be able to do collaboration with multidisciplinary teams, because failures can be associated as a result of process issues. It need not only be just confined to the material deficiencies. So he has to interact with different teams to analyze the problem as a team. Finally, the last slide which I'm coming to is the commercial aspect. I'm having this slide just to cover for the team members who are from the procurement side, because this is something which is important. So the cost variability, the cost of metallurgical failure analysis cannot be fixed. So many a times the people who are associated with failure analysis would come to cases when people say, give a lump sum for a failure analysis for a particular project. So particular projects can have anticipation of 15 to 20 failures in a time frame of 3 years, give a lump sum. So that is not possible, because failure analysis costing depends on different complexities. Some failures which may not need many tests or investigations may be of lower value, and the others might be very complex and of very high value. So it is depending on the complexity. And the root cause analysis is a far more extensive analysis, in which processes are involved, expectations which add to the cost. So when it is said that a root cause analysis has to be considered, you need to bear in mind that the cost will be higher when compared to failure analysis. So the typical mistake of a procurement department is requesting unit rates of the different test, and they say, for example, unit rate, as I told in the first case, cost variability. We can't have a unit identified rate for the analysis, but many a times they say that give a rate for tensile hardness, micro, macro, SEM, and the total cost of the failure much higher than the unit test rates, because the cost of the failure is not the cost of these tests, but it is the cost of the total package, which involves the expertise. So it is failure analysis is a subject which requires a lot of skills, a lot of analytical expertise. So you can't have unit rates and then cost of the interpretation. So asking for the rate and then pricing is questioned. This is the mistake which is carried out by all. Finally, some references for the failure analysis. These are the typical books which are very handy for a failure analyst, like Corrosion Engineering by Fontana, Understanding How Components Fail by Volpe, Volume 11 for Failure Analysis Handbook, Volume 12 for Fractography, and RCA BSI standard EN 62740. That's it for the presentation. I think we have gone beyond time, and we are coming to the conclusion. Uh, this is the email ID which is mentioned. If you have any questions, please feel free to drop email to this number, to email ID, and we'll be happy to answer your questions. Coming to the end, we will send you the booklets for the presentation, which you can refer as and when required. And we will have, if you are okay with this, we will have a quick, sorry, but quick quiz related to this failure presentation. And if I would suggest that you just complete this so that you get a feeling that uh, regarding how much you have understood the subject. So I'm sharing it in the chat box, and you can click to the link and submit it, and fill it up and submit it. That's it from my side. And let me see if we have any questions at the moment.
Excuse me.
Yes, please.
I have a question. Thank you.
Yes.
I just wanted to ask you, please, how can the one specify the exact damage mechanism RCFA among all of these damage mechanisms? We have a wide range of damage mechanisms. So how can we narrow down that each damage mechanism to reach to a conclusion or just like confirmation that this is exactly the damage mechanism that happened and lead to this failure? Is there any strategy used which can help, especially young engineers, decide these things? Thank you.
Yeah. Thank you, Mr. Mohammed. It's a very good question. And yes, you are right that just as I mentioned in my presentation, failure analysis study itself is a very detailed study, and we can't cover everything. This is just a quick presentation covering I have tried to cover analysis in this presentation, but having said that, you can't with 1 hour presentation we can't give a conclusion regarding what was the cause of failure, because I've just showed you 4 or 5 slides, and in that we have tried to conclude. But when we have done the investigation, for example, a fatigue failure, you will see typical features of fatigue failure, like ratchet marks are there. And when there are a number of cycles which are causing the failure, you can see beach marks which are evidence of the number of cycles which the component has gone through. So that is an evidence of a fatigue failure. And when you do the investigation, you will see that the failure has initiated. You can see the initiation point in the metallurgical examination very clearly from where it has. And you will be in a position to see whether if it is a fatigue failure, you should be looking for features which are related to fatigue notch stress concentration. So if it is a stress concentration like notches or a pit depth, so that has initiated the fatigue failure. So this is just with reference to fatigue. But when we talk about individual failures, you have to do in-depth investigation. Visual examination is one part of it, and going through the operating procedures, operating conditions, and if any abnormality during the operating conditions. For example, if there is a breach of the chemical which is going through the equipment itself, it was not expected to have uh, uh, microbes in the water, for example, just an example, and you noted during the water analysis that there are microbes, then we can point out that it has it and also the features supporting to those microbes. Then you conclude that the failure was because of MIC attack in the component. So this the we can't very quickly or shortly answer how can you conclude to cause of failure. What I have mentioned in the case study is just 4 or 5 slides, but that's much more than that which was involved as a part of the failure investigation, as a part of the visual examination, background information gathering, study of the background information, etc., which we can't cover in this short span of time. So, uh, does it?
Thank you, Mr.
Yeah, right.
I think, according to what you thankfully said, so we start with the visual inspection, and
Yes.
according to this, just to collect the main features, things that help us to narrow down the damage mechanism among all of these to, for example, to 2 to 3 damage mechanism. And according to these possibilities, we look for the evidence to
Yeah.
support which damage mechanism is with the equipment or any other and just like
Exactly. What we do is
in general.
we in general what we do is we uh, have when we start the failure investigation, we have 5 or 6 different uh, probabilities of the failure. We note down those probabilities of failure, and during the course of study, one by one, we overrule the ones which are not applicable, and we find which one is the most applicable case or probable cause of failure. So many in most of the times you don't say the cause of the failure is this, because end of the day it is always coming with some sort of a probability. So you need to mention the most probable cause of failure is this.
Yes, yes,
Yeah.
definitely. With the aid of techniques available, which can help us to finally decide which one is the confirmed damage mechanism.
Yes. Yes.
Yeah, thank, thank you very
Thank you.
much appreciated.
Yeah. Thank you. Thank you, Mr. Satish. You had some question.
Excuse me, was the session recorded?
Uh, no, the session was not recorded.
Okay, thank you. And will we get the slides?
Yeah. There were certs will be provided to all those who are interested to get the certs, and there will be two types of certs. Once you submit these questions which we have sent quiz, so it can be either uh, certificate of participation or attendance, or the other one can be the certificate of successful completion.
All
So
right,
will
thank you
be,
so much. I was actually asking about the PowerPoint presentation.
yeah, PowerPoint presentation cannot be shared, but the slides will be shared in as PDF to you.
All right, all right. I appreciate it. Thank you so much.
Thank you. Um, I'll appreciate if you can just submit the um, quiz, and that's it for the time being. I just wondered, we had slotted 1.5 hours and we are just touching 1.5, so it might get disconnected. But anyways, thank you once again, everybody, for your participation. Highly appreciated. And any questions you have related to the topic, please feel free to drop in your questions and we'll respond to that. Also, if you have any queries related to a particular failure investigation, we'll be more than happy to help you out for that. Thank you so much.
Thank you, Mr. Bashishta. Thank you.
Thank you.
Appreciate it.
Thank you so
Bye
much.
bye.
Bye bye.
Thank you.
Thank you, everybody. We are signing off for the time being, and we will look forward to your questions, the quizzes. Thank you so much. And also, last comment from my side will be, we will be sending you a feedback questionnaire. We'll appreciate just 3 minutes of your time to fill that, and it's just a selection of questions in Google Forms. So that's very easy. You have to just select question answers and reply back. Thank you so much. Have a good day, everybody.